All right, well, let's get going on our wireless section. This wireless section will be the last big section that we have. Hey, that's a great news, right? That's fantastic. But there is a lot to wireless. When you start dealing with wireless, you're dealing with radio technologies, and that radio transmissions happen a lot differently than electronic transmissions. And so we're not really here to become radio experts, but there are some strange things that happen in the radio world that don't happen in the electron world. And so you really have to think of the airwaves as a face of a lake, and when you drop something into it, you create waves across that lake. Now, the only difference really between that and radio waves is the fact that radio waves transmit, for the most part, if you have a unidirectional antenna, it's going to transmit like a donut. It's going to blow outwards from that transmission point, where you're throwing a rock in the water and it's just going across the face of it. There's also something happening below the surface. There's waves transmitting below as well, but we don't see those. So I'll be using over here. We'll be using some pictures quite a bit to try to show you what it looks like. So first off, let's just look at a two-dimensional rendering of the frequencies that we use that we'll be getting into for what we would call 802.11. So again, the 802 specification means that it was created initially in February, that's the 2, in 1980, and the .11 is the 11 iteration of networking. So the 802 designation is all about networking. 802.3 and 802.5 describe Ethernet and how that functions, and we don't really talk about that anymore. We used to. And 802.11 came about later and started to talk about how wireless networks function. So in any case, the 2.4 gigahertz frequency is what you're seeing on the screen there. It's about an inch long, and so when you measure a point, this upper point to here, you're going to get an inch, or if you measure from here to here, you're going to get an inch. So this is a little blown up, I guess is what I'm saying. And then when you look at the 5 gigahertz frequency, that's another part of 802.11 that we use. The 5 gigahertz is much shorter, much smaller. And so if we took a look, I'm not sure we can find this one out here, but let's look up the 900 megahertz frequency. So a lot of radios work off of that, and I'm not sure we're going to be able to find. Yeah, there's nothing here showing us what that looks like. Usually I would draw this on the board because the 900 megahertz frequency is much bigger. The frequency that, going from down to up, that frequency waveform is much, much bigger. Probably, I don't know, I'd have to guess about 6 times bigger than the 2.4. And the larger a frequency is, the more it can go through objects. And so it's kind of an important concept, a fundamental concept to me that you understand. The facts sheets, and some of the video is mentioned. So if you watch the other videos that they have and test out, they'll kind of mention it. But to me, they don't go in deep enough to help a student understand that the length of that frequency makes certain things available and not available, certain features available. Well, what do I mean by that? Well, the smaller a frequency, the more data you can put in the stream. So if we consider this the whole stream of information, we can put more data in this stream. This oscillation is happening more frequently, and you're encoding data along this. So basically, certain values along this oscillation mean certain things. And because it happens more often, you can put more data in it. And 2.4 is less. And there's really no way to get around that. You can up the speed, kind of, what we would say up the throughput by condensing the data. But other than that, it's going to carry the same amount of data because there's only so much you can do with this waveform or this one. And so if you've got a 900 megahertz and it's happening like this, you probably can't even see my mouse pointer, but if it's happening from the top of your screen to the bottom of your screen, then you're not able to put as much data into that stream. However, the great thing about it is that the bigger the bandwidth, the more objects it can go through. And so this is all a very simplistic way of looking at it. We're not trying to make us radio experts, but if you look at the 2.4, anything that's bigger than this frequency, and again, this is blown up, you got about 2 inches here instead of 1 inch, so it's about half this size. Anything that's bigger than that, the frequency is not going to go through. So if you said, I have got my wall and it's got a brick in it, and that brick is more than 1 inch thick, it's going to totally block the signal. Now, truthfully, there's a lot to the density of the metal. For instance, you can have steel or iron that's not very thick at all, and it's going to disrupt that frequency. So it's not just how thick is it, it's also how dense the material is and what the material is made of. That's not why we're not going to get into all that. But basically, the simple rule is that 2.4 gigahertz is going to be able to travel through, say, your indoor walls pretty easily. It'll disrupt it a bit. So if you've got a big house, it's not going to make it through there. But when you think of EAC and you have to build, a government building differently than you build your home, the walls in EAC are thicker. And so what's going to end up happening is that 2.4 signal is going to bounce around. And definitely the 5 gigahertz signal is going to have to bounce around in your home. And so the 5 gigahertz signal, while it can carry more data and it basically is faster for us to use, it can't go through walls or objects the way 2.4 can. And 900 megahertz, which is what a lot of the standard in-home phones use, it can go through walls very easily. And that's why, if you remember those days where you just had your mobile phone, not your cell phone, but a mobile phone for your house, you could pick up that signal all over the place. Because voice doesn't take a lot of data to transmit to begin with. And then on top of that, it can go through your walls, your brick walls. It can go through a skinny tree. It can go through a lot of things to get to its destination back and forth. And so that wavelength is important to remember, and that's why I start with that. That's why I show it before we really get into wireless and we talk about it, because you have to understand that the wavelength affects how much data you can transmit on it, but it also affects what it can go through. And so when you start talking about 3G, 4G, and 5G, it's like, well, how do they make that stuff faster? Well, they just keep adding more wavelengths, and they're sending data on different wavelengths. And the more of those wavelengths they put together, the more data they can send to you. And of course, there's always that question of, well, how dangerous is that? And to me, anything that's focusing, for instance, you're holding your phone up to your ear and you're always on your phone talking to somebody, that those wavelengths are coming out of your phone antenna pretty strongly in order to hit some tower that's 2 miles away. That's a lot different than having a 2.4 gigahertz radio in your house and your computer's talking to it and it's only, not even 20 or 30 feet away, maybe 50 feet away at the most. So that's why also your phone will burn through battery power like crazy when you're trying to use your cell connection, because it really has to push those radio waves out of that little tiny device strongly in order to get to some tower that is miles and miles away, where your computer doesn't have to do that. It knows that 2.4, that 5 gigahertz radio is in the next room. It doesn't have to just push it as strongly as it can. So you have the wavelength, the waveform, how big that is, and then you also have the power at which you're pushing that out, and those things affect how far it can go and what it can do. Now, just for an example, there's actually, I don't know if you've ever watched shows on this, but there's, in order to talk to submarines, our submarines that hold these nuclear missiles are the largest deterrent for war in the world, because nobody knows where those subs are. Not even the President of the United States knows where they are. So they may know, oh, there's someplace in the Pacific, but they don't know where in the Pacific. They are actually told to go and run out there for months at a time and just be there and not tell anybody where they're at, so that nobody could find them. If there was some kind of nuclear war, they could just surface and launch their missiles, or get close to the surface and launch their missiles, and nobody would be able to stop them from doing it. That's, if you're another country, that's scary situation. How they receive the launch codes is kind of interesting. They actually use a wavelength that is a mile long, and that wavelength is so huge that it can go through the earth. And so you've got that top point to the bottom point to the top point. Again, that wavelength is so huge that it can actually just go straight through the earth. You would obviously realize that really can't carry a lot of data, but it can carry a set of codes that basically they can look in a book, and they can look at that code and go, oh, that means launch against China, and then the next code would come in and give them a location. So that's kind of pretty cool technology when you think about it. And that's why if you're driving on the road, you switch to AM radio, right? You can pick up AM radio many, many miles away. And most of us that are a little older, know that if you turn on AM radio at night, you can pick up stuff from Montana or someplace else, because it's actually that wavelength that's blowing out. And I'll pull up a picture of what it looks like. Just reflects off of the atmosphere and then comes back down. So, it's going from Montana to Arizona, and it comes in very clear without a problem. That's thousands of miles away, but that's because the wavelength is that big. And that's why AM radio is not, stereo. The sound quality is not there, because you can't encode as much data on that wavelength. There's a bunch of wavelengths, and as a matter of fact, that's what you're tuning into, right? So when you tune to FM 107 point something, that's like tuning to 2.4 gigahertz, right? So we're going to look at those channels in a little while, because there's a bunch of channels within 2.4 and also 5. So I don't really want to lose this, so let's do another search. For waveform, maybe donut. There might be something that'll actually pull up. Well, some donuts. There you go. That's not really going to help us. Waveform. It's kind of, these are all flat waveforms. They're all showing it two-dimensionally. Let's put in omnidirectional. Antenna. There's a bunch of omnidirectionals. Omni meaning that it's going to push that signal out everywhere, every direction. Unidirectional, or those are usually flat antennas, and that's what we see on the cell towers, is a combination of flat antennas. Let me put waveform in here. Just try wave. Nope. Oh, there we are. Yep. This is a good example. That's a GIF. So if this is your omnidirectional antenna and you're looking down on it, then this is how it's going to push that out through the air. Just to remind everybody, you can't hear somebody's voice except for the reverberations through the air. So this would be more of a side view. You'd have an omnidirectional antenna in here, and that signal would balloon out around that antenna. And so, in a lot of what we do, this is another top-down. So it's blowing out in a circle, and this is primarily where these signals are going to be pushing out for the strongest reception. So in your house, you got a bunch of those little antennas, right? And they're creating all these donuts that are emitting out of that, and they're bouncing off the walls and basically trying to cover your house in this signal. So if we look at unidirectional, see if it's going to have a waveform for us here. This is a good example of a unidirectional. And so they're showing you your satellite, but it doesn't matter what it is. It could be a flat panel or slightly curved or whatever, and it tries to take that ballooning effect that happens naturally and pushes it in one single direction, thereby pushing that further. And so if you go around and you look at the cell towers, you'll notice that they're flat panels sitting next to each other, because what they're trying to do is out of each of those panels, they're trying to push that signal as far as it'll go, instead of just using an omni, which won't push it as far. So when you look at what cities and counties use all over the place, they have all these big tall antennas, and those are omnidirectional, and those suckers will reach hundreds of miles. And that's what emergency services needs to use, so that they can actually be in your basement and pick up a radio signal in somebody's basement where their cell phone can't pick that up. Different wavelength, different way of pushing off the antennas in order to make that happen. But because it's that bigger wavelength, you're not getting as much data. So if your cell phone was even equipped to use it, it wouldn't get a very good signal. You wouldn't be able to use data or anything. The other thing that you need to know about is that there's actually channels that you can use and channels that you can't. So the government, like in the 700, 800 megahertz range, not gigahertz, megahertz, they restrict that for use of government facilities. They can all use it, but if you get on those channels and you start to send out signals on those channels, they'll come and they'll arrest you, they'll shut you down, because they're meant for emergency services and military use. So that's kind of just a brief on how the radio technology is. Like, that's the base. Now we're going to get into how that all operates and the little channels that are in between there, because radio's been around a long time, and Wi-Fi, wireless, whatever you want to call it, is not going away anytime soon. It's always going to be slower than what we're using on the cables, because cables are always taking that signal directly to where it needs to be. But we're going to use wireless for the foreseeable future. All right, so in the next video, we'll start getting into the test out material.